Hello everyone. So today we'll be starting with continuing with the trees. So today is day two of solving trees problems in this 30 days DSA live grind. So these will be there will be no session tomorrow, and I am saying this right to inform you. So there will be no session tomorrow, but from day after tomorrow there will be sessions as usual. Right? So I hope you understand. We'll be starting in just 4 minutes, right? 8:35 p.m. start. We'll be starting at 8:35 p.m. Mm, Excuse me. First thing, let's understand today's concepts. Firstly, we'll be having parent and uh, child concept, right? And then we'll be solving some of the problems in lead code. Now, yesterday uh, got we have understood what is a binary tree, right? So if any node is having 0 or less than less than or equal to two nodes, right, then it is called as a binary tree, right? Now the traversals will be having the breadth first search traversals and depth first search. So if we go to the depth first search, we'll be having depth first search will be having pre-order traversal and in order traversal, then post order traversal, right? So in pre-order traversal, we'll be having the root node on the first, right? Root first here, root middle, post order means root will be at the last. But when it comes to left and right, root, left, right, that's it. Now, left, root, and then right. Here, left, right, and then root. So, I think it's clear for you all. Pre-order traversal, in-order traversal, and post-order traversal. If not, you can go and check the yesterday's live session. I have explained clearly with the code and also the algorithm. Now, let us see about the breadth first search. Uh, Nothing but the level order traversal technique, right? We go level by level, right? And we call it as level order traversal. So it is quite clear, level order traversal. So if you understand these things, breadth first search and depth first search in trees, it would be easy when you go to graphs, right? So I hope you understand what I want to explain, right? Let us see. Now let us look at the maximum depth problem. Maximum depth of a binary tree. I'll be sharing you the link of the problem in the description. Sorry, in the live chat. We'll go and check it. So you can see here. So this is how we solved it using breadth first search, right? So I think we got submissions here. This is the first one using depth first search, right? We are just using the recursive code, uh, you know, the maximum you get by going to the left and going to the right. We select the maximum from it and add one to it and return, right? So I hope it's clear for you. And if you have any doubts, please let me know. Right? Okay. Now let's look at the code of breadth first search, how we solve it. Uh, Again, let's just recap it. Let's just recap our code, breadth first search code. So we started with a queue. We initialize a queue and push root into a queue. After that, initialize the depth with 0, and then while queue is not empty, while queue is not empty, in the loop, we'll just go with size is equal to q dot size, and uh, we'll just iterate into this size and get the node. Uh, Let me tell you, for I is equal to 0, I is less than size, we just go with node as q dot front. Let me just write it as take the front node and pop. Let's just take it as node itself, naming it as node. And if if there is left node, there is left node, then push into queue. Do the same with the right node. If there is right node, push into queue, right? So this is the loop, and then as we got a node, we'll just increment the depth and at the last return the depth. That's it. This is how you solve maximum depth of a binary tree, right? I hope you understood this. So if you have any doubts, please let me know in the live chat. Yes. So let us go to the next section of this live session. So let's go with parent and child concept for right. So let's take it parent and child concept, right? So if you take a tree, binary tree, 1, 2, 3, 4, and then 5, if you see this 4 is called the child and 2 as the parent node, right? And this 2 is the child of the parent node 1. Let's just recap this. This will be our root node, and uh, these will be our leaf nodes, right? Leaves, right? These will be our leaves. Now, these trees are just like a family, right? We can just say it as a family. Now, this will be the grandparent of this node 4, right? So this will be the parent and this will be the grandparent, right? Now, one node can have a left child and a right child. The node above them will be their parent. Now, the concept is in a binary tree, each node can have at most two children. So let me write it for you. In a binary tree, in a binary tree, every node, every node or each node can have at most, I am saying that at most two children, and they are called it, we call them as left and right. Now, the root node will not have any parent, has no parent, no parent, right? So let's take the real tree example. If you see, if you see the tree, root of a tree, you know, let's take this root. Now, there will be a trunk, I think. So it will be called as trunk, and these trunk will be having some of the branches. Let us take only two branches for now. Now, these will be having another two branches, right? And then this will be having another two branches. Now, this will be having only two branches, then only two branches, right? So if you see, I'm just taking only two branches every time. I hope you are clear why I'm taking only two branches every time, right? Right? I think you are clear why I'm taking only two branches. Now, every branch, I'm saying that it is having only two leaves, right? So it is having two leaves everywhere. So how you think about this, right? So it is having one root. If you see, it is having one root and it is having some of the branches. Let's also, what is, let's also number them at every branch, right? So, okay, that's good to, that's good to explain this, right? Okay, now let me say this will be our root node, and everywhere you know, this and then this and then here and then here, then here and then here, right? uh Now if you see, everywhere I got some of the branches, right? Now these branches, from this I got this and then this, and these are having two and these are having two, and then two branches here, two here, and then again two here, again two here, again two, right? Now these again having 2, and then let me just zoom it so that you can understand it clearly. Yes. And every leaf, you know that, every leaf will be a node. That's how I'm thinking, like, right? So every leaf will be a node, and we are having this much of nodes. I hope it's clear that how we are going with trees concepts, right? By taking the real life example. Now let's take the example, right? So here, if I just take this, right, this is having this, and then this is having like this, and then this. Now these are having two children. Every one of it is having two children. Yes, every node is having two children. Now these are having again uh, two children, right? So two children, two children, and here also two children, here also two children, right? Okay, so it is just like a real tree, and this will be the leaves of those last children, right? So this will be the last generation of this tree. We'll just what we'll do is just we'll just uh, reverse it. We'll just reverse this tree. That's it. We just got a tree from this. Now, if you see, instead of taking this complex tree, let us just take 1, 2, 3, 4, and 5. So these are considered as children of one. A binary tree for if I take an example. If I take an example, then 1, 2, 3, 4, 5. So I thought, right, the depth will be as height. Many of us might think that depth as height, but if you see, there is a clear difference between height and depth. Height will be 2. Height will be 2. But if you come to the depth, here the depth is 0. Wait a second, right? If we talk about height, it measures from uh, measures from bottom. Depth of 1 is equal to 0, depth of 2 is equal to 1, and depth of 4 is equal to 2, right? Now, height of 4 will be 0. Let us take this as no, right? Wait a second, right? We are at 1, 1, right? Now, depth of 1 will be 0. Now, what will be the depth of 2? Depth of 2 will be 1. Depth of 3 will also be 1. Now depth of 4 will be 2. Now let's consider the height. Height of 4 height of 4 is how much of it is having. If I say, let me take it as height of 4 is 0. I'll tell you how it goes. You'll understand how it goes uh, to the extent of 1. Now height of 2 is equal to 1 and height of 1 is equal to 2. Why? Because from 1 I have 2 steps. Now depth of 1 is set as 0. How much far is it from the root? And uh, if you see here, how much, let me write depth as depth is how much far is the node from the root. If you calculate it from the leaves, so height is height is height is something like a bottom up measurement. Height is how far a node is from the bottom. Else write like top and bottom so that will not be confused, right? From the top here, from the top. I think it's clear like what is depth and what is height. Now let's go with what is a diameter of a binary tree, right? If height is how tall a tree is, the diameter is how wide it can stretch, right? Between the two farthest nodes, right? The diameter is the longest path between any two nodes in the tree. These tree concepts is, much more than the previous concepts like prefix sum algorithm, hash maps, and also do some problems like sliding window and two pointers, right? So, what is the diameter of a binary tree? This is a concept. Diameter of a binary tree. Hello, Arshik bro. I hope you are doing great. Right, thanks for attending the live session. So, Longest path between any two nodes in the tree is known as the diameter of a binary tree. Now, the path may or may not pass through the root. Right, this is the another thing. The path, it is not guarantee, or we need not to be sure the path should pass through the root. May or may not pass the pass through pass through the root. Right? Now, we will be measuring this diameter not by the nodes, instead measured by measured in edges. In edges. I think you are clear with these will be nodes, and those which connects the nodes will be our edge. Right? Now, let's take an example here. Firstly, we have 1, 2, 3, and 4, 5, 6, 7. Let's take the longest path. Let's come to this 4, right? Let's come to this 4 and go to 2 and then to 5, and from 5 to 6, right? Or you can also go to 4 and then to 2 and then 5 and then 7. So the longest path I'm seeing here, I can see, is 4, 2, 5, 6, right? Now the number of edges you can see is 1, 2 and 3. So the diameter will be 3. But how can I know the diameter in a code, right? How can you approach it? How can you just approach it recursively, right? Now, let's go with the recursive approach. If you have any doubts till now, or if you want to share anything, just comment in the live chat. So, how can you write a code for this? That's the part which we'll be discussing about, right? How can you even write the code of this diameter of a binary? We need to go to a node which is the farthest, and also the other node which is the farthest. Now, thank you, brother, Bhaskar brother, for commenting. Thank you so much. This is the day two, and if you are watching this live session, please do subscribe to our channel and like this. Right. Let us look at the code or the algorithm for diameter of a binary tree. We'll be going on, right? If you have any doubts, please let me know. But don't you think the diameter is wrong here, right? If you just take 31256, that's what I am thinking, right? Right. Yeah. So instead of taking 4256, why can't we just take 31256? Let us see. Let us check, can we take it, right? I'm taking 3, I'm taking 3, 3, and then going to 1, and then going to 2, and then to 5, and then you can go to 6. Now, let me write it over here. I just went from 3 and then to 1 and then to 2 and then to 5 and then to 6. How many edges do you see here? I can see one, two, three, four, 4 edges, right? So what will be the diameter, right? The diameter will be the 4 number of edges. Between any two nodes, the path may or may not pass through the root, but it has passed through the root, right? Now it is measured in edges. Okay. Now how can we write a code for this or the algorithm? Find height function, right? Now you're starting with the right. Now you're starting with the root and the diameter. Now If root is equal to null, then return 0 there itself. Now left height will be the same recursive code. Will call the find height with root of left root of left comma diameter. Now the right height is equal to find height of root right comma diameter. Now we'll be updating the diameter. Now the possible maximum path through current node. Now as we got through the height, so if you see, we just if there is left node, push into Q. If there is right node, push into Q. Take the first node, right? So we need to update the maximum every time, max depth of every time. So let's look at the DFS approach, depth first search approach. If you see, we are taking the max depth of root left and max depth of root right and taking the maximum of both of them and adding 1 to it, right? So here we'll be doing the same thing again, right? So the diameter will be here, the diameter will be maximum of diameter comma left height plus right height. Now in the last we'll return 1 plus maximum of left height comma right height. As I have said already, it is the number of edges which declares the height. So we'll be just returning 1 plus maximum of left height and right height. Now you might ask me that why the diameter, why when we are considering the diameter, we are just taking instead of left height plus right height. We are not saying that uh, left height maximum of the diameter comma left height or right height. Let me take this example 2, 4, 5 and then 6. If you see for this, left height is equal to 1, right height is equal to 2. Now the diameter only for this will be 1 plus 2, right? So we'll just add left height plus right height. That's why we'll just add left height plus right height. That's how we solve the uh, diameter of a binary tree problem. I'll share you the link of the problem, right? Don't worry. Excuse me. So it is also an easy problem, right? I'm just giving you the link of diameter of a binary tree problem. So you can go there and check it, right? So if you have any doubts till now, please let me know. So given the root of a binary tree, return the length of the diameter of the tree. Diameter of binary tree is the length of the longest path between any two nodes in a tree. That's what I said here. The longest path between any two nodes in the tree. I think I need to change my handwriting, right? So it is not uh, a good enough. So, however, this path may or may not pass through the root. That's what I wrote. The path may or may not pass through the root. Now, the length of the path between two nodes is represented by the number of edges between them. The same thing measured in edges. That's it, right? So 1, 2, 3, 4, 5. Okay, let's calculate. Here it will be 3, 1, 2, 5 or 4, 2, 1, 3, whatever it might be. 5, 2, 1, 3. However, 4, 2, 1, 3 or 5, 2, 1, 3. Okay, now root is equal to 1 comma 2. Then there will be only one edge. Number of nodes in the tree is in the range 1 to 10 power 4, and node value can be from minus 100 to plus 100. Let's look at the algorithm which we wrote here. We just wrote the pseudocode find height. We are calling the find height, right? We are calling the find height function. So we are having the value and then the left and then the right. Now let's start with int diameter is equal to 0. We'll call the find height function with root and diameter is 0 itself and return d at the end. Now first height find height tree node of root comma int diameter right. Okay, now if root is equal to a null pointer, return a 0 there itself and int left height. Let's write it in full names. Int left height is equal to find height of root left comma diameter, and here it will be right. Okay, right. Okay, right. Sorry. Right height is equal to find height of root right and diameter. We just passed it. Now diameter is equal to maximum of diameter comma left height plus right height. Now return 1 plus maximum of left height comma right height. So let me run the code first. I hope it executes. Yes, let me submit it. Yeah, I think it's clear for you. If you have any doubts, please let me know in the comment section. Right, so this is today's concepts and all. No, it's not. It's not over. It's not over. Is there the where is the cursor? So we just did a revision on breadth first search and also the depth first search. So the binary tree. You can ask your doubts. There will be a doubt session, right? Let's calculate the uh, you know time and space complexity here. So the time complexity we are just going with every node, right? So it will be for this, it will be the time complexity will be big of n. And what about the space complexity? The space complexity we are just going with the height of the tree, go of h. Yeah, I think it's clear for you. If you have any doubts, please let me know in the live chat. Okay, let's take an example like a beautiful one. Let us see. Let me tell you, what if I have a tree like this? One, two, three, 4, 5, 6, and then 7. Now, what I want to do here is I want to mark every level, right? I just want to, connect the same level nodes. Nothing but populating next right pointers in each node. Let me tell you how it works. One, wait a second. Let me just copy it. Now, how it will be is 1 next will be null, 1 next will be null, and 2 next will be 3, and 3 next will be null, and 4 next will be 5, 5 next will be 6, 6 next will be 7, 7 next will be null. That's how it works. So each level's nodes are linked horizontally. Let me write it over here. Each level's nodes are linked horizontally, right? Okay. What is the problem name of this? Let me tell you, I need to search for it. I just remembered a concept like this. populating next right pointers in each node. Lead code, lead code, lead code 116, populating next right pointers, populating next right pointers, right pointers in each node. Okay, I'll be giving you the problem link in the live chat. It will be pinned in the comments in the live chat itself. Right, go and check it. You can open it, and you can open it and start thinking about the problem. How can you connect these, right? So we are given with the next pointer for every node, right? So we are given a perfect binary tree where all leaves are on the same level and every parent has two children. Okay, that's a good thing to know. The constants are really, they have given us in the description itself. So every parent has two children and the leaves are all leaves are on the same level, right? It's not like some leaves on the second level and some leaves on the third or fifth, like all leaves on the same level, right? Now, every node will have the value left and right usually, but in this in this problem, we are also given with next pointer. I haven't solved it before previously. I just remembered some concept like this and I just explained you this. Populating next right pointers in each node. This is a classic BFS problem. All right. I'll tell you how we can solve it. But if you have any doubts, please let me know in the comment section and let me know what will be your approach for solving this. Now we need to go level by level, right? We need to populate every level with next pointers. Every node need to have the next pointer. Need to We need to just make the next pointer to the next node, adjacent node. So we just need to go with the we just I'm just thinking like we need to go with the breadth first search. Let me know what do you think in the live chat. Yeah, populate each next pointer to the point to its next right node. If there is no next right node, the next pointer should be set to null. Initially, all next pointers are set to null. Yeah, they have took the same example, right? 1 2 3 4 5 6 7. 1 2 3 4 5 6 7. Yeah, they are on yeah, that's It's the same thing. 1, 2, 3, 4, 5, 6, 7. Okay. We are given we are given with above perfect binary tree. No. Our function is to populate each next pointer to point to its next right node, just like in figure B, as they have given, shown in the figure B. Now, the serialized output is in level order as corrected by the next pointers with hash signifying the end of each level. Now, there might be a case that the root will also be empty, the tree will be also empty. So the number of nodes will be ranging from 0 to 2 power 12 minus 1. Now the node value from minus 1000 to plus 1000. How can we go is, I'm just looking, excuse me, I'm looking for a breadth first search approach, and I'll be implementing the breadth first search, of course. But how can we go with it? Go with it, right? We can get the nodes. Let us initialize the BFS. How does it work, right? In BFS, we'll be having in the queue will have 1, and then this after this 1 will be having 2 and 3, 2 and then 3. For this 2 we'll be having 4 and then 5, 4 and then 5, and for this 3 we'll be having 6 and 7. Do you see anything other than this? We'll just remove every time a node, 5, 6 and then 7, 6 and then 7. So the queue is empty now. Okay, I think you got it. So uh, yes, we can just remove these nodes until the size. So 2 and 3, right? They can be connected. And then as you remove this 3, you can just connect the 4 and 5, and then 6 and then 7. Let us see how, right? Let us go with, let's go with the algorithm, right? So let us initialize, let us initialize a queue and name it as queue. Push root into queue. Now after that, we'll push a null pointer after it, right? Null, push a null, right? Now, while the queue is not empty, queue is not empty, pop the front node and name it as pop front node and name it as current. Now, if current is not null, then we'll just set current next as q dot front. So the next right node is in the same level, right? Now, then push the then push its children into the queue. Then push children into queue. Now, if current is null, we just reached the end of level. If current is null, we reached end of level. I think you got it right. First we got 1 and then null. So as you get null, that means we are end of the level. Now here, if Q still has elements then push another null. So after that we'll be having 2 and then 3 and then null pointer again into the queue. So we have this algorithm. How can we code it? So we got the algorithm, but let's go. How can we code it? Node connect, right? Now, if there is no root, then we'll just uh, return null pointer, right? So if there is no root itself, then return null. Now q, which has node into it, q. Now q dot push the root node and also the null pointer while the queue is not empty. So if you see, push root into queue, then push a null pointer. We just did initializing the queue, pushing root into the queue, and push a null pointer. We are using the null pointer to indicate that we have gone through every node in that level, right? If there is a null, that means we got to the end of the level. There is no nodes in the level, right? Now, while this queue is not empty, take current as queue dot front and remove that from the queue. If there is a current, then current next is equal to queue dot front. If there is a left child, then queue dot push current left. If there is right. Now, else if q is not empty, then q dot push null pointer. As I have said it previously, pop front and name it as current. We have done it here, current. We have just removed that from the queue itself. Now, if current is not null, that's why we just said that if current, that means this is not null. Current value is not null. If current means, that means it is returning 1 if it is true. How does it become true? Is if it is not null or if it is not a 0. While we are going with nodes, If it is not null, it will be returning true. So if there is a current node, then we can go with it. Now if current is not null, now current next is equal to q dot front, and then push their children into the queue. We have done it, left and right child. Now if current is null, we reached end of level, right? If Q still has elements, uh, push another null, right? So as we have completed the level, right? If Q is not empty, then push null pointer into the queue and then return root. I hope the code runs. Yeah, let me submit it. But till then, each node is visited once here. Each node is visited once, only once. So it is a breadth search algorithm. So the time complexity will be big of n. Now the space complexity, we are just taking a queue. So big of n. I hope it's clear for you. If you have any doubts, please let me know in the chat box. I think it's clear for you, right? If you have any doubts, please let me know in the chat box. Hello, Sumuk bro. So thanks for attending the live session. As you have asked me if you are following any DSA sheet, can you please link it here? I'm not specifically following any DSA sheet. I'm just solving the frequently asked and the standard problems in lead code, right? All the interview problems which are mostly asked in many companies. So but when I was starting the DSA in second year, right, I just went through Stiver's A to Z DSA sheet. Let me paste the link here, and also it's Neat Code 150 is also a good choice. Yeah, brother. I've shared the link. Let me also share you the Neat Code 150 sheet. So these are the best looks, right? To solve on to crack interviews. You can also follow me in LinkedIn. Yes, at 10:30 p.m. We'll be starting resuming our problem solving. Till then, you can ask your doubts. So let's solve this problem. Path sum, I have given the link of this problem in the live chat. Go to the pinned comment, you can find it. So we are given with a binary tree, given the root of a binary tree and an integer target sum. Return true if the tree has a root to leaf path such that the set that root to leaf, not to the middle. They asked us to find whether there is this target sum from the root to the leaf, right? So if it is there, then return true. If not, return false. So how can we solve this problem actually? So a leaf is a node with no children. Uh, we already knew that, right? Okay. Let us look at the example given here. 5, 4, 8, 11, 13, 4. Let's just copy the image. Yes. So if you see this, path sum, problem number 112. Uh, so that what is the target given here? Target sum is 22, right? So the problem number path sum 112. This is an easy problem, right? So path sum. This is a problem number or problem name. Let us see this. So in example 1, they are given with the target is equal to 22. Let me take the same example. 5, 4, 8, 11, 11, 7, 2. Here 13 and then 4, 4 and then 1 here. Let us do solve this problem, right? So current sum, I am saying it as 0, starting with 5, so it will be 5. Next go to 4, 9. From 4 go to 11, 9 plus 11, 20. From 11 go to 7, then 27. Now this is the sum at 27. This point we went to the leaf node. Now is it equal to target? No, right? So it is not equal to the target sum. So what we'll do, we'll just backtrack from 7 to this node 11. Now instead of taking to the left, going to the left, let's go to the right and add sum of 2. I'll get 22. Now that's the same case, right? So when we started with 5, we went to 4, right? From 2, let's backtrack to 11. Do I have any other? No. From 11, then go to 4. Do I have a right node for 4? No. Now, let's go to 5. So, at this 5, instead of going to 4, let's go to the 8. 8 plus 5 is 13. However, we'll be returning true as we have explored this path, right? But let us see 13. Let's just understand the DFS approach. So 13, and let's go to the left from 8, then I'll get 13 plus 13, nothing but 26. Do I have any other nodes here? No, it is a leaf node. Is 26 is equal to 22? Nothing but the target sum 22. No. So what we'll do, we'll just backtrack from 8. Let's go to 4. So 13 plus 4 will give us 17. Now from here I can go and add 1. So 17 plus 1 is 18. Do you see any other paths? I went this path, this path, this one, and also this one. Only one path is valid, and that path is 5 4 11 2, right? So that's how we solve this. 5 4, so 5, so sorry, 0 and then 5, 9, then 20, and then 22 by following this path. Okay, now how can we code this up? That's the main thing here, right? So this will be the last problem we'll be solving today, right? We'll be going to the doubts session, and if you have any doubts, please don't hesitate to ask me in the live chat. Let's write the algorithm, right? First, we need to do a depth first search, right? So for that, we'll use a recursion function where it will have the root and then the target sum, nothing but the target sum, and the current sum, right? Now here, if the root is null, if the root is null, return false, right? That's the base case. Now if the node is a leaf, if it is not having any left or right child, if node is a leaf, then check whether current sum current sum plus root value is equal to target. If so, we'll return true there itself. Now otherwise we'll recursively check both left and right subtrees, right? Else check both left and right subtrees will pass current sum plus root value to each call. Now if if any any subtree has if any subtree has a valid path, then we'll return true there itself. Return true, right? Let's write the code for this. We'll write this, we'll call this recursion function in the main function, right? So we'll start coding this up. First, let us write the recursion function. Let's write the recursion function here has path sum bool recursion function. We are taking the tree node root and int target and also int current sum. Now here, if wait a second, if root is equal to null, then return false there itself. Now if root left is equal to null and also root right is also equal to null, that means we have got a leaf node. We'll just return target is equal to current sum plus root value. Now return a recursion of root left comma target comma current sum, or current sum plus root of value. As I said, we'll just pass at each time current sum plus root value to each call. Now the same thing again, recursion root of right and then target and then current sum plus root value, right? Okay, now we'll call this function return recursion of root comma target comma 0. Let me run the code first, hope there will be no errors. Target, sorry, it should be target sum let me submit the code. So yes, so if you see, I'm going through only every node in the tree. So totally it would take me, like, the time complexity will be big of n, and we will be going with the recursion stack, uh, right? So the space complexity will be big of h, where h is the height of the tree. So that's how you solve this problem. And if you have any doubts, please let me know in the live live chat, right? Okay, I think there are no doubts from your end.